starting from the second order, because we already done everything about the first order differential equation. And this time we're going to look at the linear. And then into the two different pieces. One piece is called the homogeneous and the other piece is called non-homogeneous. And for the n order, for example, the second order linear, it could be in the form of the A2 y double prime plus A1 y prime and plus A0 y equals the gx. Okay, if gx equals 0, we call the homogeneous equation. If gx is not 0, it's called non-homogeneous. And then for the coefficient A1, A2, and A0, it could be the function. So A0, A1, A2. This is just for the second order. For the second order, for the coefficients, the A0, A1, A2, it could be the constant term or the function term. So for now, for the earlier part of chapter 4, the coefficients, they are constant. And that's going to be pretty much what we're going to talk about in 4.3 and 4.4. When we get to the 4, 5, 4, 6, and later on, going to be coefficient as a function, but still within the category of the homogeneous and non-homogeneous. Okay, so just to identify how to see this as a homogeneous or non-homogeneous, you look at the right-hand side, whether it's 0 or non-zero, and that has to be the function of the independent variable. Okay, most of the time we do the y in terms of x or y as a function of the x. So y and its derivatives term will be all together on the left-hand side. The right-hand side, just the function of the independent variable or 0. And then by the superposition principle of the homogeneous, now we're going to target the homogeneous. Okay, for the homogeneous, which gx equals 0, or the right hand side is 0, the theorem, the first one, which is about the superposition principle. Okay, for the homogeneous, so we have the solutions. When we have the second order, we have two sub-solutions like y1, y2. Those will satisfy the same differential equations. That we did a whole bunch of verifying or identifying whether the given function is a solution or not. Okay, so for the superposition principle, for the solution like y1, y2, okay, so we can, if both of them are solutions, both of them are solutions of the given equation. So we can say the solution y can be rewritten as the linear combination of the y1 and y2. For the linear combination, that means you can write it as a sum with the coefficient like C1 and C2, where C1 and C2, the relationship that you put them together as a linear combination is not 0. Otherwise, you're going to get a trivial solution, which every differential equation has trivial solution no matter what. Okay, for the homogeneous. So we do not pay attention to the 0 solution or the trivial solution. We're going to look for the case of non-zero solution. For the non-zero solution, say y1, y2, they can be put together as a linear combination as C1, Y1 plus C2, Y2. The notation C1, because it's just to be together with the solution Y1. When you work on the problem, just consider one constant or one coefficient as a real number. The notation could be anything as you like. You could do like C star or the D or whatever the notation that you like to use. But in general, we just do like C as a constant. So C1 with the solution Y1, C2 with the solution Y2 as a general pattern. Okay. So the superposition principle said you can write all sub-solutions as a linear combination of the same differential equation. That's what about the homogeneous superposition principle. And then for the y1 and y2, as they are solutions, the c1 y1, if you take just like y1 and multiply by some constant, you still use that term, that function to satisfy the same differential equation. That is the corollary of the theorem. So the y1 is just the fundamental function, or we can call it just the basic function. When you multiply the number to the solution, it's still the same solution. It still satisfies the solution. Okay. When we get to some examples, well, this is the example, the later part of the under the corollary, show you the example. For example, I'm gonna go to another page here. So if like y1 equals x squared and y2 equals x squared natural log x are both solutions of the x to the third y triple prime minus 2x y prime plus 4y equals 0. So we know that both of them satisfy the same equation. But if you multiply y1 by some number, the same, it still satisfy the same differential equation. Like if you do with just the generic y1 or x squared, we know y1 prime is 2x and y1 double prime is 2, y1 triple prime is 0. So bring it into the equation, it will satisfy because it's given by the problem. So this can be 0 minus 2 times x. This is y prime. Yeah, y prime is 2x. And then plus 4 times y, which is x squared equals 0. Yes, 0 equals 0. Check. And by the corollary said, if you multiply y1 by some number, like for example, I multiply by 3. So 3y1, which is 3x squared. So when I find the derivative and keep going, 3y1 prime, I would use this as y1 star. Let's see, y1 star. So gonna be 6x, this is prime, y1 star double prime is 6, and then y1 star triple prime is 0. And let's check whether it's true or not by the corollary. So x to the third times y triple prime, that's 0, minus 2 times x times y prime, which is 6x, and then plus 4 times the y1 star, which is 3 x squared. Yes, it's still 0. So that's pretty much the proof or the verification that you have the y1 equals x squared. You multiply any number to the x squared, you still use the new form of the solution to satisfy the same differential equation. Okay, and that's I'm gonna point out to this again when we get to the 4.2, the reduction of order technique. Okay, so that's the first part. And then the linear dependent and independent of the solution. As we write it as the linear combination, all solutions must be linearly independent. Otherwise, you can write one in the form of constant multiple of the other. Like we say 3x squared and x squared, they are linear dependent. Okay, they are linear dependent.